Our next lesson is going to be on vectors, and in this lesson we're going to look at vectors and vector addition. So, as we said, vectors and vector addition. So, a vector. First thing, a value that's measured, a real number that gives only one piece of information about a quantity is called a scalar in the sense of a scale. And a scalar only gives magnitude. So, for example, if one were talking about how tall you are, you would say that I am something like 2.1 meters tall. And so if that were the case, then that would be a scalar value. It gives the magnitude of your height. Or you were to say, how far is it from here to Des Moines? That if you're giving just the distance, in that case, that you would say it's 15 miles. That's a scalar. You could similarly say, what's the volume of this bathtub? Or what is the temperature outside right now? All of these are scalars. Magnitudes that tell you, it gives you a real number that tell you information about a quantity. But not all values work that way. Sometimes you have a case of something where you have two pieces of information that go together. Most commonly, and the case that we'll use in this class, in a case where you have something that has a magnitude and a direction. Say, for example, describe what your velocity is. Well, you could say I'm going 5 miles per hour, but that really doesn't give a total amount of information because in reality you're going some direction. You're going 5 miles per hour west, 5 miles per hour northeast, 5 miles per hour 5 degrees away from the sun. And so in that case is that when you have something that has a magnitude and a direction, something has two pieces of information that are sort of bound together, really can't be separated, that's called a vector. And so this unit will deal with this idea of what vectors are. Technically, a vector is any piece of information that's more than two, and so like in a simple mathematics sense, you also could talk about matrices that have two values in them. So for example, if I had like 3 and 1 like that, that's actually a vector as well, though it's not the type that we'll really deal with for this class. If you take math later on, or if you take science getting farther, especially if you get into quantum mechanics, then you'll see this notation, this use of the term vector. But for right now, we're really interested in the magnitude and the direction. So let's take a look. I have two arrows down here, and these represent vectors. And so in a vector, you have two things. You have a magnitude and you have a direction. So for this one right here, I can measure the length of this vector. The length of a vector when drawn out shows its magnitude. Like let's say this one is 3, whatever the units are here. Maybe we'll say inches. I don't know if that's what it is or not. It certainly isn't on your screen, but it might be on mine. So we have a magnitude here. We have a direction. The direction of this one would be, say, to the right. Or if this were a north, south, east, west, we'd say this would have a direction of being east. And so that would be a way of expressing this particular vector. That would be 3 inches at east to show that it's at some direction here. And so this would be the information you'd have in your vector. In this case, east isn't a number. We'll come out with a way on our next slide of actually writing out values of this using a heading system. But for right now, just sort of take what we've got here. Let's say we've got our other vector that's right over here. This one is a little bit longer. Let's say that it is 4 inches long. And so as being 4 inches long, we would then have to give a direction as well to give the completeness on this vector. And so that would be, say, northeast. And so this is 4 inches northeast would be sort of the full vector that we have here. Vectors, you have to have both pieces. You can't describe it simply in terms of one. And so vectors are useful for speeds. They're useful for accelerations. You know, you were accelerating. Which direction were you accelerating? To describe acceleration, you need to have both things. Force. If you push on something, how hard did you push? I pushed 50 newtons. Matters which direction, doesn't it? You know, if you push something 50 newtons in the wrong way, then you're doing exactly the opposite of what you meant to do. If you're pushing it perpendicular, then you're not doing anything useful. So these are common cases where we'll be using vectors in physics. As notes, it's often useful for a quantity which has both magnitude and direction to be expressed as a vector. We could technically write them separately, but as we're going to find out is that to combine things that are vectors, it's critical that you leave them as vectors. You can't split them up. They just don't work when you do that. And so force, velocity, two examples of this. Let's take a look at how we might describe direction, because that's important for doing this. And we will be using what is called the heading system. This is what's used by pilots commonly. Note that this is different from what you'll use in terms of directions in math. The heading system basically works like this. If you had, say, north, south, east, and west, north is 0 degrees, east is 90 degrees, south is 180 degrees, west is 270 degrees. If you ever go to an airport, you'll notice that there are numbers written on the ends of the runways. And those runways numbers are, if you basically have a runway which is north-south, on one end will be 36 and on the other end will be 18. The reason why is basically the 18 shows 180 degrees down here. 36 shows 360 for north. If you look on the runway, if you have an east-west runway, it'll have on one end, it'll have 9, on the other end, it'll have 27. If it was something where, so basically what it does is drops off the 0 off of that. That way pilots can see which direction the runways are angled. This is the heading system. If I had a vector that, say, went up like this, how would I find the angle? Well, you always measure it from north. And so in this case, north down to here would give me some angle. And let's say that's 45 degrees. 45 degrees. And so in this case right here, I would say that that particular vector has a heading of 45 degrees. If I had a vector that instead was over here, let's say that we find that this angle right here is 10 degrees, then I would say that this vector right here has a heading of 260 degrees, because it's not quite to 270, it's just slightly, it's 10 degrees before it, and so it's at 270 degrees. If I had a vector that was up like this, and let's say that this angle right here is going to be 70 degrees, then I would say it's going to be 270 plus 70, which will give me a heading of 340 degrees, and so on and so forth. Pretty much for this class, anytime that we describe a vector, we're going to give a direction in terms of a heading. And so if I say a vector is at 0 degrees, you know it's pointing due north. If I tell you it's at 185 degrees, you know it's 5 degrees just west of south. So 185 degrees would be something like down there, okay, where this angle in here is going to be 5 degrees. All right? And so that's sort of what we've got going here. And so this is how we'll describe vectors in terms of this. Typically, we'll write them out like this. And just FYI, if you're writing out to show a variable as a vector, usually you just put a little arrow on top of it like that. And that shows this is x. It's a variable. We don't know what it is, but it's a vector. And so we could say, like, for example, we might have something that is 4 meters per second. And we'd say at 30 degrees. So 4 meters per second at 30 degrees would basically mean that we have it's pointed up in this direction right here, where that angle in there is 30. It's almost impossible to see right now, and this has a magnitude of 4. So let me actually erase some of that so we can sort of see what's going on there. So if we're doing, so we said before that our vector is going to be 4 meters per second at 30 degrees. You do it like this. So we'd say this angle in here is going to be 30 degrees. I'll draw an arrow to make sure we can sort of see it a little better, 30 degrees. And to show that it's got magnitude of 4, we put a 4 beside it here. Meters per second. If you could fit it, try to get your units in there with it, because that's quite useful there. And so that's how you'd go about writing out vectors. That's how we'd sort of go figure out the direction on that. So, onward. Let's suppose we want to add 2 vectors. 2 people are pushing on a table in slightly different directions. How do you find out what their total is? Let's say that I've got someone who's pushing on a table at 40 degrees and someone else who's pushing on a table at 235 degrees, and one person has a force of 50 newtons, the other person has a force of 60 newtons. What's the total force in the table? Well, if they were both pushing in the same direction, this would be easy. You just add the 2 up. That's what you do with scalars, and so, but unlike scalars, vector values can't be simply summed. You can't simply add them up because they're not in the same direction. It simply doesn't work the same way. It's not possible to add them up that way. So if I have 2 people who are pushing on something in different directions, I've got to add them up using a technique of vector addition, which works very differently than scalar addition. Scalar addition is simple. You just add them up. Vectors don't work that way unless they're pointing in the same direction. So vectors must be added head to tail with the sum of the 2 vectors, which is called the resultant, being the vector proceeding from the tail of the first added vector to the head of the last. So let's say we're going to add these 2 vectors right here. So we're going to add this vector and this vector. And so when we do that, basically what we do is we're going to take the one vector and put it, so its tail is at the head of the next one here. So I'm going to take the tail of this guy right here, move it up to the head of this guy, and so that's what I have right here. And so you can sort of see how I've taken this vector and I've sort of shifted it up to here. And that's what I get over on this side. So you can sort of see how that works here. And so this is how I get my picture that's right over here. And so that's how you start off by adding them. Usually what you'll do is, since you can't move around vectors on paper very easily, is you'll usually redraw them. Redraw the two vectors so that one is summed with the other one. Now, when you do that, the resultant is basically going to be the vector which starts at the tail of the first one and goes to the head of the second one and creates a vector like that. And so effectively our answer of this guy plus this guy, this vector 1 plus vector 2, is going to equal to our blue vector that's shown right there. That's how you'd go about adding those guys up. That's how this works. If we wanted to add a third vector, if it said, nope, now I want you to add, say, this guy right here. The way you do it is you take this guy and add him to the sum of the other two. And so in this case, he would start right here and head on down that way. And so our resultant vector now, given this, would basically be from here to here. It always goes from the bottom of the first one, the tail of the first vector, to the head of the last vector. And so you do one vector first, then you do the second vector, then you do the third vector, each one starting where the previous one ended, and then the total vector, the sum of all those vectors, simply being from the tail of the first one to the head of the last one. That's basically how this works. And so you can sort of get an idea on how that sets up. Now, I want you to notice something. It really actually doesn't matter which order you do these in. We could have, because in this case right here, we actually added this one first, then this one. We could have done it the other way. If we did it the other way, I'll try to sketch this out. We'd have a vector that looked a little bit like this first, and then we'd have this other vector like that. And when you do that, you can see that actually it creates basically a parallelogram between the two. If drawn properly, I didn't draw the exactly parallel, but it should create a parallelogram. And so from that, you can sort of see it really doesn't matter. As long as we started at the tail of the first one and go to the head of the last one, it's going to end up being the same regardless. But that's how we add up vectors. That's how we find our resultant sum vector. If we have multiple vectors, we just keep on adding them up. And so, if I have 5 different vectors, I could say I got this vector, and then I got this vector, and then I've got this vector, and then I got this vector. And what's my sum? What's my total vector? My resultant? It would be from the tail of the first to the head of the last, right like that. That's my vector sum. You always add up vectors that way. So that's basically how you set up vector addition. So let's take a look at an example. One man pushes a box with a force of 45 newtons at 90 degrees, while another pushes with a force of 33 newtons at 180 degrees. What is the total force on the box? I will tell you this. In all physics problems you will ever do, especially mechanics problems, the first thing you want to do is you want to draw a picture. Draw a picture of what this looks like. And so in this case right here, it says we're pushing on the box with a force at 90 degrees, another pushing the force at 180 degrees. And so in this case, you can sort of imply that we're looking at this from the top. And so if we were to take a look at this from the top side, you can sort of see we have a box that's right here. We have one fellow who is pushing on the box with a force of 45 newtons at 90 degrees. And so 90 degrees would be basically due east. And so that's what we have right here. Another pushes with a force of 33 newtons at 180 degrees. 180 degrees is going to be down here. And so that's 33 newtons. Now, to what's the total force? To add these up, we have to add up vectors head to tail. Right now, the way we've sketched this out is that these vectors are not head to tail, they're tail to tail. You can't add vectors that way. So to add these up, we're going to have to resketch. And so I'm going to draw this one right here, 45 newtons. And the next one, 33 newtons. We're going to start it at the head of the other one. And so 33 newtons right here. And so to find the resultant would be from tail of the first to head of the last one. So that's going to be over here. And so that's going to be our resultant right there. That's how we're going to have to work this out. Now, to find the total force, we have to take a look at what we've got here. We've got a shape which is a triangle. In this case right here, the 45 and the 33 newtons, it's going to be it's fortunately for us in this case, going to be a right triangle, which makes the math nice and easy. And so in this case right here, since it's a right triangle, we know the two sides. We can just use the Pythagorean theorem to solve here. And so the length of our last one, which total force, which we'll just call F right here, so that F squared is equal to, so it's, a squared plus b squared equals c squared. So the hypotenuse F squared is equal to 45 squared plus 33 squared. And so, if we break out our calculators on this, we say 45 squared plus 33 squared, get our answer, which is 3114, and then take the square root of that. If I can do that. My calculator is not playing nice with me. So 45 squared plus 33 squared, take the square root of that, and I get 55.80. So I get that the net force is 55.80 newtons. Is the magnitude of the force. Now, force, though, is a vector. And so technically, we need more than just what we've got here. Now, before I go on here to find that angle, we do need to check one other thing, which is significant figures. Here, we had 45 to start with, 33 to start with. That's going to be two significant figures. For this class, there are rules that are out there for finding significant figures with angles. We're not going to worry about them. For the purpose of this class is that round your angles to the 10th of a degree. So whenever we're dealing with in degrees, we'll get to radians later on this year. But for right now, so round angles to tenths of degrees. And generally is that being said, is your angle, we're not going to let that affect the overall number of significant figures. So for right now, it's only going to be dependent on our magnitudes, which are 45, 33, both two significant figures. So our total force here is 56 newtons. So that's going to be our force. But we need to find direction. How do we find direction? Well, we're going to be looking for what this variable is. Typically, is that whenever you're looking for a variable that's an angle, we're going to call that theta, Greek letter theta. Sort of give you a little bigger version here. I don't usually draw them very well, but basically lowercase theta looks a little bit like that, like a zero with a line through it. And so that's the variable we'll typically use for angles. If we have a second variable, so this is the equivalent of x, second variable we'll use phi, which sort of looks like that. And then I guess if we need a third one, like z, we'd have psi would be the third one. So those are three Greek letters. Normally we're just going to use theta. That's going to be our big one right there, so just sort of be aware of that. So we're looking for theta here. How do we find theta? Well, trigonometry time. And so in this case right here is that we know the two sides. We know the opposite and the adjacent side. And so if we know opposite and adjacent, that's going to be looking towards tangent. And so we know we have tangent of theta, which is what we're looking for, is equal to opposite, which is 33 newtons, over adjacent, which is 45. And so you'll have to take an arctangent on that, and make sure if you're working this out that your calculator is set to degrees, because otherwise that will give you trouble. And so we're going to set up arctangent of 33 divided by 45, or inverse tangent. Arctangent is probably, I prefer to use that form simply because inverse could mean 1 over tangent or cotangent. So I'll usually call it arctangent for that reason. And so this gives us that theta is equal to 36.253, which we said we're going to round to the tenths place, so 36.3 degrees. And so our final answer down here, we already figured out the magnitude of this particular vector was 56 newtons. Our final answer is going to be that the force is going to be 56 newtons at 36.3 degrees. Note that for a force, being a vector, you really need to have all of that in there. So 56 newtons at 36 point, that's 0.3. Oh, wait, there's a slight problem here. This is not correct. I'm sorry. This is not actually at 36.3 degrees. I want you to see if you can see why on this. I'm getting ahead of myself. The reason why this is not at 33 degrees, 36.3 degrees, is that if you look at this angle that's in here, this angle is not from our zero heading. Zero heading is up here. If this were pointing at 36.3 degrees, it would be going at an angle like that, but this is going downward. This isn't 36.3 degrees away from zero heading. This is 36.3 degrees away from the 45 Newton force. And the 45 Newton force is at 90 degrees. And so for our total, we're going to have to add that to 90. And so we say plus 90 degrees to get our total here. And so we get 126.3 degrees is going to be our actual heading here. And so 126 0.3 degrees would be our final answer. And so you do need to watch out for that, because that's one thing that will ding you pretty quickly, just like it did me right there, is that you always need to go back and express your result in terms of a heading. If you were given one, start with a heading, and all the ones you're going to get in this class are. So you've always got to take it back to the original coordinate system, the original heading that things started off with. And so our final answer here is that we have someone pushing with 45 newtons at 90, 33 newtons at 180. We're going to get a total force of 56 newtons at 126.3 degrees. And so that's what we have there. Onward. Taking a look as we go forward here, our next problem. Let me get to it. It's a pilot flying a plane with an airspeed of 210 miles per hour is flying a plane with an airspeed of 210 miles per hour at a heading of 105 degrees. With the wind blowing at 10 degrees, he discovers that his total speed, his ground speed, is 225 miles per hour. How fast is the wind speed? Just a little about terminology here. When you talk about planes, their airspeed is basically their speed with respect to the still air. So if there were no wind, that's how fast they'd be going. The wind speed's pretty obvious, speed of the wind. The ground speed or total speed is basically their total speed. It's what, if you were on the ground and watching them somehow like had a radar gun, how fast it appeared to be going. So if I had a plane that had an airspeed of 100 miles per hour and then had a wind that was blowing in the same direction at 20 miles per hour, their ground speed would be 120. That would be the speed. If you're on the ground, you'd see them going 120 there. They'd cover literally 120 miles per hour with respect to the ground. So just some information there. So first thing to do, let's sketch this guy out. And we have, has an airspeed of 210 miles per hour at a heading of 105. And so let's just sketch this out. We're going to draw an axis here first. We know it's 105. 105 degrees would be between 90 and 180, 15 degrees off. And so that means that this vector will probably be somewhere down here. And so we know this angle right in here is going to be 15 degrees. We know it's going to be 210 is going to be our magnitude of that vector. Now the wind is blowing at 10 degrees. So we're going to set up another little axis here. That way we can get the angle here. Since the wind is blowing at 10 degrees, we're going to put it up here. We don't know the magnitude. So we don't know how long to make this. But we do know that the total speed, the ground speed, is 225. And so if the ground speed is 225, that would mean if we take this vector right here, sketch that out, this one right here is 225. We know that. This is the picture we have so far. Question is, how fast is the wind speed? So we're sort of looking for this variable right here. We're going to call it v for speed here, just to keep things straight. Now, sometimes you sketch out a triangle like this. It's not always obvious what the sort of picture looks like. So sometimes it's helpful to sort of resketch it to make it more triangle-like. And so in this case right here, I will resketch. So I have this vector right here, which is 210. I have some other vector, which is... once again, sketching this out, which is going to be at 10 degrees up this way. And so a little arrow in there to show that's 10 degrees for that little angle in there, not the whole angle. And then I know that my other vector that comes out here is going to be 225, except that should come from up top. 225. All right. So from this vector, from this picture, can we figure out what the lengths are here? Well, first question, is this a right triangle? That's letting us do our normal trig stuff. And the answer is no, it is not. There's no 90-degree angle anywhere in this triangle. It doesn't appear there is. We know that this angle right here that's inside that's 10 degrees off the wind speed, we know that there's 15 degrees. Now, if you remember back to your geometry days, I'm going to zoom in a little bit on this guy, on this 210 guy. And we're going to bring him down to this axis, down like that. Since this angle in here is 15 degrees, gosh, it's not really writing very well. That means that this angle right in here can't be 15 degrees, but rather it would be 90 minus 15 degrees is 75 degrees. And if that's 75 degrees, then remember we have this nice little opposite angle theorem. So that this angle in here is 15 degrees because we have two parallel lines. And that means that this angle right in here is going to be 75 degrees, just like that. And so if that angle is 75 degrees, that means that this total angle inside this section has to be the 75 that's over in here plus the 10 that's in there for a total of 85 degrees. So we're close to 90 degrees, but not quite. So we have 85 degrees in there. We don't know what this angle is. Looks right now it should be a little less than 15. We don't know what this angle is, and so we've got a little bit of a problem, because to find our solutions we can't use Pythagorean theorem because it's not a right triangle. We don't have a whole lot of other information. In this case right here, our technique is that we're going to have to use one of two trig rules for non-right triangles, the law of sines and law of cosines. So in this case right here, we're going to use law of sines, and law of sines basically says this: if I have some triangle, which I will once again just sketch out a general triangle that doesn't sometimes even look like a triangle. We'll say it has sides A, B, and C. Interior angles are going to be capital A, capital B, and capital C right there, if you can see any of that. That basically, so the opposite angle to a side, it gets the same letter. That we basically would say that we have that sine of angle A over A, side length A, equals sine of angle B over side length B equals sine of angle C over side length C. I guess that should be a lowercase b right there. Like that, and so on and so forth. Well, only three of them because only three sides in a triangle. So this is how we're going to set this up, because if you look at things, this is useful if you know a side and the angle opposite to it. And here we do, because we're able to combine all those sides over there. And so by doing this, to set this up, we're going to say the sine of the 85-degree angle over the length of that side, 225, is going to be equal to, well, we only know one other side length. That's the 210, and our little angle that's up in the upper right. And so this is going to be equal to sine of our unknown angle, theta, over 210. And so, once again, let's break out the calculators on that to find what our missing angle is up there. And so we would say that sine of 85, once again, make sure you're in degrees, divided by 225 times 210 gives you a total of 0.929. And now we have to take the arc sine of that. And so arc sine of your answer. And in doing so, I get 68.4 degrees on the nose. And so that means my theta is equal to 68.4 degrees. Now, if this angle in here is 68.4 and the other angle is 85, we know we can add that plus 85, take that from 180 degrees to find the other angle. So I get 26.6. So this must be 26.6 degrees. But I want you to notice something. We said before this total angle in here, this one right here, is 15 degrees between the 210 and the axis. If that's 26 degrees, that means we sort of missketched this guy a little bit. And note that this isn't really a problem. It just means our picture's a little bit off. Technically, when we sketch this, it should have looked more like this. So I'll try to sketch this up here. So we had this guy down here, is that our next vector, the one at 10 degrees, actually went like way up there. And so this should go up to meet up with it, to finish that up. But this really doesn't affect us here. We can still work this out. We'll still get the same type of angles here. We'll still get the same result. We just know that our that we're going to end up with it's going to be slightly different than what our picture was. But that's fine. You'll see that that's not an uncommon occurrence. So to finish this off, we're going to put this back into our law of sines, because now we can find that missing piece over here, this v that's hiding over there that we're looking for. And so to do that, we're going to say that we have sine of what we know, so sine of 85 degrees over 225 is going to be equal to sine of the angle we just found, which is the 26.6 degrees, over the opposite side to that, which is our v that we're looking for. And so based on this, we can go ahead and we can say that we have we solve for v, so we multiply v up to the left side over here, so that's probably the easiest way to start this off. So I multiply v up there, and that cancels v down here. That way we can go ahead and simply say sine of 26.6 and then times 225, then divided by sine of 85. And I get for that 101.1 for v. 101.1. Units here are going to be, it's miles per hour. Yep, miles per hour, mph, which is an alternate way of writing that out. Significant figure-wise is that it has an airspeed of 210. That has two significant figures. 225 has three. So our answer should only have two significant figures, which would round this just down to 100. Or if you want to be on the safe side, you would say 1.0 times 10 to the second. That would be a nice way to make sure you preserve your significant figures. Miles per hour. And the angle we already knew, which was at 10 degrees. Yes, at 10 degrees. So we already had that in here. And so this right here would be what we have for our final answer, is that the wind speed is 100 miles per hour at 10 degrees. Technically, it just says how fast. So that could be either a velocity or a speed. Speeds typically are just the magnitude of the velocities. But that depends. You sort of have to look at it here. Is that look at how your answer choice, what it's asking for. It's always better to put more information than too little. So I may have been able to argue how fast here could have been just a speed, but in this case we put the whole velocity out to be on the safe side. So 100 miles per hour at 10 degrees is the wind speed, and so that's how you might set that up. So from there, that gives us one more here. An antelope runs for 450 meters at 70 degrees, then 320 meters at 190 degrees. How far is the antelope away from his starting point? So we start off here with an antelope. So he starts here, he runs at 70 degrees, he runs 450 meters, and the angle in here is going to be 70. Then he's going to run 320 at 190 degrees. 190 degrees would be just slightly inside right over here. And so we know that this angle that's in there is going to be 10 degrees because this 190 is 10 degrees off of 180. And we know it has a length here of 320 meters. 3 meters up there too. Our resultant, how far he is from his starting point, will be along this vector right here. And so that's what we've got. So once again, do we have a right triangle? The answer is no, we don't have a right triangle. Can we figure out any of the angles in here? Well, we know that the angle that is over here is 70 degrees, which means that this whole angle back to the axis has to be 70 degrees. But we know that this little angle, as we said, is 10, which means that this interior angle in here would have to be 70 minus 10, so it's 60 degrees. So geometry is coming back to being useful again. And so here we have this. Now we can't figure out any other angles. We don't know any other sides for right now. We're looking for the distance he is away from his starting point. So we're looking for the length of the magnitude of that vector, just that one right there. Just how far, just a distance here. So we can't use law of sines because we don't have any opposite angle with one of its sides, which means we have to use law of cosines. Law of cosines is basically this. Once again, same type of setup where we have sides A, B, and C and angles that are opposite those sides, also A, B, and C, is basically this. C squared is equal to A squared plus B squared minus 4A be cosine of angle C, like that. And so that's where we're going to start there. I just made my thing disappear. Plus I made a mistake on that law of cosines. So resketch this really quickly here. So what we have here is the antelope starts off right down here. He's going to run 450 at 70. So 450 at 70 degrees. That's a 70 degrees. Then he's going to run, same here, coming down like that, 320, and at 190, which is 10 degrees in there, which means we've got a resultant that comes down here. We've got this angle right here, which we already figured out that has to be 60 degrees in there. But back to our law of cosines again, and I made a mistake on that last time. So C squared equals A squared plus B squared minus 2AB cosine of angle C. Okay? And so that's our law of cosines. That's what we're going to use here. And this works if you have two sides and the angle in between them. And so to set this up, we would say that our length here, which we said was going to be our distance right there, that our distance squared is going to be equal to A, which is 450, plus B, which is 320, minus 450 times 320 times cosine of our angle in between, which is 60 degrees. Okay? And doing so, that we should be able to find what and I just don't know what's happened here. It just disappeared on me again. Nope, got it back. So no clue what just went on there. This thing's acting up. So let's go ahead and take the calculators here. We're going to look for what D is. So in this case, we have 450 squared, so 450 squared plus 320 squared, minus 450 times 320 times the cosine of 60 degrees. And so when we get that, I get D squared is equal to 232,900. And so to find the square root of that, ends up with 482.59. And this unit is going to be in meters for what we have here. Significant figures, 450 has 2, 320 has 2, so our answer should have 2. And so the distance he is away from his starting point is 480 meters. If we wanted to figure out what his displacement was, which would include direction as well. Typically, a distance, how far, just talks about just the magnitude. But displacement will describe both the magnitude of the distance that he's moved and the direction. Then we need to find an angle as well, which we could do at this point, because now that we have this side, we could then use law of sines, since we know this length right here. But he's 480 meters away from his starting point, and that's how you'd use law of cosines to work out a basic vector problem.